In this video, we will tackle a real-world pharmaceutical scenario and use manual calculations to determine the probabilities associated with the binomial distribution. Imagine you're a researcher at a pharmaceutical company that has developed a new allergy medication. Initial trials indicate a 90% success rate. However, before releasing the medication to the public, you decide to conduct a smaller-scale test with a sample of 15 patients. This sample test raises several questions that can be answered using binomial probability, like: what is the probability of the medication working for exactly 12 out of the 15 patients? What is the probability of it working for at least 14 patients? What is the probability that the medication fails for more than 2 patients? By analyzing these questions, you can gain a deeper understanding of the potential outcomes of the sample test and make informed decisions about the medication's distribution. Before we tackle the pharmaceutical problem, let's quickly grasp the fundamentals of the binomial probability distribution. The binomial distribution is a statistical model used to predict the probability of a specific number of successes in a fixed number of independent trials, where each trial has only 2 possible outcomes and a constant probability of success. In a nutshell, the binomial distribution is a statistical framework that describes the probability of obtaining a certain number of successes in a series of identical, independent trials, each with only 2 possible outcomes, success or failure, and a consistent probability of success. The probability mass function of the binomial distribution is given by this formula, where n is the total number of trials, k is the specific number of successes, p is the probability of success on a single trial, and n choose k is the binomial coefficient. Let's now apply the binomial distribution to our pharmaceutical scenario, where each patient represents an independent trial with 2 possible outcomes. The medication is either effective or not. We have a fixed sample size of 15 patients, and based on clinical trials, we assume a constant probability of success of 90% for each patient. By applying the binomial probability formula, we find that the probability of the medication being effective for exactly 12 out of 15 patients is 0.1285, or 12.85%. To determine the probability of the medication being effective for at least 14 patients, we calculate the cumulative probability for 14 and 15 successes using the binomial probability formula, resulting in a probability of 0.5490, or 54.9%. In this case, we're looking at the probability of the medication being ineffective for more than 2 patients. We are essentially shifting our focus to the failure outcome. The original probability of success, that is medication being effective, was 0.90, and the probability of failure, that is medication being ineffective, was 0.10. So, when calculating the probabilities for 0, 1, or 2 failures, ineffective cases, we would indeed use 0.1 as the probability of success in the binomial formula. Now, using the complement rule of probability, the probability that more than 2 patients experience failure is 1 minus the probability of 2 or fewer patients experience failure. The calculated probability is 0.8159, or 81.59%.